Welcome to Physical Chemistry. Today we are going to explore the kinetic gas equation. Imagine a room filled with a million tiny, super bouncy rubber balls that never stop moving. They constantly smash into the walls, creating a steady push. This is exactly what gas molecules do inside a container to create pressure. We will learn how to connect this invisible microscopic world of bouncing molecules to the visible macroscopic world of pressure and volume that we can actually measure. Let us dive in. To begin our journey, we must understand the difference between macroscopic and microscopic properties. Macroscopic properties are the things we can easily measure on a large scale using instruments, such as the pressure and volume of a gas. On the other hand, microscopic behavior refers to the hidden details of the gas, like the mass of a single molecule, the total number of molecules, and how fast they are flying around. The beauty of physical chemistry is finding ways to link these two worlds. The kinetic gas equation is the ultimate bridge that allows us to predict everyday macroscopic measurements using the invisible atomic details. Now that we understand the goal, let us look at the mathematical bridge itself. This is the fundamental kinetic gas equation. It comes from analyzing the physical force exerted by particles bouncing off the walls of a container. In this equation, P stands for pressure and V stands for volume. On the right side, m is the mass of a single molecule, n is the total number of molecules, and c is the root mean square speed of those molecules. Notice how it connects the two worlds. If the speed of the molecules increases, which happens when the gas gets hotter, the pressure must go up, assuming the volume stays the same. Before we see where this formula comes from, let us see it in action with a concrete example. We are given a container with a volume of 2.0 cubic meters holding 10 to the power 24 molecules. The mass of each molecule is 5.0 times 10 to the negative 26 kilograms, and their root mean square speed is 400 meters per second. We need to find the pressure. We start by taking our kinetic gas equation and dividing both sides by the volume to isolate the pressure. This shows that pressure depends directly on the mass, number, and squared speed, and inversely on the volume. Continuing with our calculation, we substitute all the given numbers into our rearranged equation. We multiply the mass of a single molecule by the total number of molecules to get the total mass of the gas, which is 0.05 kilograms. Squaring the speed gives us 160,000. Multiplying these together gives 8,000, which we then divide by the volume of 2.0, and finally divide by 3. This gives us a final pressure of approximately 1,333 pascals. This means the gas exerts a relatively low pressure on the walls compared to the normal atmosphere around us. Now that we have successfully used the formula, let us understand exactly where it comes from. We will build this equation from scratch by looking at just one molecule inside a perfect cubic box with a side length of L. Imagine this single molecule flying around and hitting the right wall. It bounces back perfectly, so its velocity changes from positive ux to negative ux. The change in momentum is the final momentum minus the initial momentum, giving us 2 times m times ux. To find out how often this happens, we calculate the time between collisions. The molecule travels back and forth across the box, a total distance of 2L, divided by its speed ux. Moving forward with our derivation, we use Newton's second law, which states that force is the rate of change of momentum. By dividing our momentum change by our time interval, the twos cancel out, and we find the force exerted by one molecule is m times ux squared divided by L. But a gas has n molecules, so we add up the forces from all of them. Since molecules move randomly in all three dimensions, x, y, and z, there is no preferred direction. The average squared speed in just one direction is exactly 1/3 of the total squared speed, c squared. This is a crucial step in connecting one-dimensional bouncing to three-dimensional reality. This brings us to the final steps of our derivation. We substitute our 1/3 relationship back into the total force equation, replacing the sum of individual speeds with the total number of molecules n multiplied by 1/3 of the average squared total speed. Now we have the total force. Pressure is defined as force divided by area. The area of one wall is L squared, so dividing our force by this area gives L cubed in the denominator. Finally, we recognize that L cubed is exactly the volume of our cubic box, V. Multiplying both sides by V gives us our final result, the famous kinetic gas equation. We have successfully bridged the microscopic and macroscopic worlds. So we have proven that our main equation holds. This brings us to another useful form of the equation. Often, instead of knowing the mass of a single molecule and the total number of molecules, we simply know the density of the gas. Density is a very common macroscopic property. If we multiply the mass of one molecule by the total number of molecules, we get the total mass of the gas. And as we know, total mass divided by volume is exactly what density is. By substituting density into our equation, we can create a beautiful, simplified version that directly relates pressure, density, and molecular speed. Let us look at the mathematical form of this relationship. By replacing the mass over volume term with the Greek letter rho for density and rearranging to solve for speed, we get this formula. The root mean square speed, c, is equal to the square root of 3 times the pressure P divided by the density ρ. Conceptually, this tells us that if you have a very dense gas, the molecules are likely moving slower for a given pressure. Conversely, at a high pressure but low density, the molecules must be zipping around extremely fast to create that force. Before we move on, let us see this density formula with a concrete example. We are given a gas at standard atmospheric pressure, which is 101,325 pascals. Its density is 1.2 kilograms per cubic meter. We are asked to calculate the root mean square speed of the gas molecules. Because we are given pressure and density directly, this specific formula is the perfect tool for the job. We will plug our known values into the equation to see just how fast these molecules are moving in the air around us. Continuing our calculation, we substitute the pressure of 1,01,325 and the density of 1.2 into the formula. Multiplying the pressure by 3 and dividing by the density gives us 253,312.5 inside the square root. Taking the square root of this number gives our final answer of approximately 503.3 meters per second. Physically, this means that in a gas with normal atmospheric density and pressure, the molecules are zipping around at over 500 meters per second, which is actually faster than the speed of sound. Now that we have calculated average speeds, we must ask an important question. Are all the molecules moving at the exact same speed? Think about cars on a busy highway. A few are driving very slowly, a few are speeding dangerously fast, but the vast majority are traveling somewhere in the middle. Gas molecules behave exactly the same way. Because they are constantly crashing into each other, they speed each other up and slow each other down. We cannot track billions of molecules individually, so we use statistics. The Maxwell-Boltzmann distribution is a mathematical map that shows us exactly what fraction of molecules are moving at each possible speed. This brings us to the mathematical equation that describes this traffic map. This intimidating-looking formula is the Maxwell-Boltzmann distribution function. Let us break it down. The term f of v represents the probability or fraction of molecules moving at a specific speed v. Capital M is the molar mass, R is the gas constant, and T is the absolute temperature. The formula has two competing parts. The v squared part at the front tries to make the probability go up as speed increases. However, the exponential part at the end forces the probability to drop to zero as speed gets very high. This mathematical battle creates a beautiful bell-like curve. Let us visualize what this mathematical battle looks like. Here, we see the Maxwell-Boltzmann distribution curve. The horizontal axis represents the molecular speed, and the vertical axis represents the fraction of molecules traveling at that speed. Notice the tall, narrow blue curve representing a lower temperature. Most molecules are clustered around a specific speed at the peak. Now look at the red curve for a higher temperature. As the gas heats up, the entire distribution shifts to the right and spreads out. This visually proves that at higher temperatures, molecules are generally moving faster, and there is a much wider variety of speeds present in the container. Looking closely at that distribution curve now, we can identify three very important types of speeds. The first is the most probable speed. This corresponds exactly to the highest peak of the curve. It is the most common speed, just like the most common speed of cars on a highway. The second is the average speed, which is simply all the speeds added together and divided by the number of molecules. Finally, we have the root mean square speed, which we used in our kinetic gas equation. This is a special average that gives more weight to the faster molecules, and it is directly tied to the kinetic energy of the gas. Now that we know what these three speeds represent conceptually, let us look at their formulas. All three formulas look very similar. They all involve the square root of the gas constant R, the temperature T, and the molar mass m. The only difference is the number inside the square root. For the most probable speed, the number is 2. For the average speed, it is 8 divided by pi, which is roughly 2.54. For the root mean square speed, the number is 3. Because 3 is the largest number, the root mean square speed is always the fastest, followed by the average speed, with the most probable speed being the slowest. Before we conclude, let us calculate all three speeds for a real gas to see this order in action. We will look at oxygen gas at a room temperature of 300 Kelvin. The molar mass is 0.032 kilograms per mole, and the gas constant is 8.314. We start by calculating the most probable speed. We plug our values into the formula with the number 2 in the numerator. Multiplying the top and dividing by the molar mass gives us a volume inside the square root. Taking the square root gives approximately 394.8 meters per second. Continuing with our example, we next calculate the average speed. We use the exact same values for temperature, molar mass, and the gas constant, but this time we use the specific formula containing 8 divided by pi. The math inside the square root evaluates to roughly 1,98,000. Taking the square root of this gives us 445.5 meters per second. As we expected from our mathematical rules, this average speed is slightly higher than the most probable speed we just calculated. Finally, we calculate the root mean square speed for our oxygen gas. We use the formula with the number 3 in the numerator. The value inside the square root becomes 2,33,831. Taking the square root gives our final answer of 483.6 meters per second. This confirms our rule perfectly. The root mean square speed is indeed the highest of the three. These calculations show exactly how fast the oxygen molecules you are breathing right now are moving around the room. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that the macroscopic pressure of a gas is simply the result of countless tiny molecular collisions against the walls of a container. Second, the kinetic gas equation is the mathematical bridge that perfectly predicts this pressure if we know the mass, number, and speed of the molecules. Finally, we discovered through the Maxwell-Boltzmann distribution that molecules do not all travel at the same speed, but rather follow a predictable statistical pattern. Together, these concepts form the absolute foundation of our understanding of the gaseous state. Great job following along.